Okay, this video is going to be about buffered solutions and how things work as buffers. Now, you probably have heard the word buffer in the past, where it's sort of like a shield or a little leniency towards some things, and a buffer does pretty much the same thing. So, a buffer in chemistry is actually a solution which resists a change in pH when another acid or base is added. Okay. This is going to consist of a weak acid or a weak base and a salt containing a common ion of its conjugate. Okay, so more or less this is going to be the common ion effect, but we're going to speak in it in terms of its buffering tendencies. Okay, so an example of this would be you're dealing with a weak acid base pair. And ultimately, a buffer needs to have an acid to neutralize the OH. So you would add something like sodium hydroxide. There needs to be a weak acid present in order to take away the hydroxides in the solution to avoid making the pH change. And you would need a base to neutralize the H+. So like if you add hydrochloric acid, how will the base come in and take away the proton so it doesn't affect the pH, okay? So how would we create a buffer? To create a buffer, ultimately what you're going to do is you're going to add a weak acid to the salt of that acid, okay? So you're just going to add a weak acid to the salt of the base. So an example of this would kind of be like what we did in section 17.3. I would have acetic acid and sodium acetate. So these two together would form a buffer, okay, where the acetate ion will react with the hydrogens and shift back to make acetic acid, where acetic acid here can react to get the hydroxides. Okay, so how does a buffer work? So I'm going to talk specifically about a weak acid. Okay, so I'm going to specifically talk about how a buffer works as a weak acid. Okay, so let's digest here a little bit. So in the past, I've written generic acids as like this, okay? And then we can write the Ka for this to be H plus times A minus. Okay, so this is nothing that you haven't seen before. Now what I'm going to do is I'm going to show you how we're going to derive for how the buffer reaction actually works. So I'm going to solve for H plus here because that's really what I care about. So when I solve for H plus turns out to be equal to Ka times Ha over A minus. Okay, so then you're talking about the relationship of the starting conjugate acid with its counterpartner, so its conjugate base. Okay, so then if we're making a point here, so then the pH is determined by the Ka of the weak acid and then the ratio between the weak acid and its conjugate base. So let me write that. pH is then determined by the Ka of the weak acid and the ratio of the weak acid to its conjugate base. Okay? So therefore, what happens is, I'm going to come down here because I don't want to use that up here. So then what happens is, if I have the reaction HA in equilibrium with H plus X minus, or not X minus, A minus, sorry. What happens is, if I add a strong base, okay, so let's say that I add sodium hydroxide to this mixture. Ultimately, since it's a strong electrolyte, it'll just be the hydroxide that we care about. Sodium has no influence on the pH. Okay, so then what will happen is this H plus will react with the OH minus, and then what do you make? Well, you make H2O. Okay, so then you're not changing the pH because this H plus can deter the hydroxide from affecting the pH. Okay, so then you have the OH plus HA in equilibrium. You'll make H2O and the conjugate base. Okay, so then if you add the hydroxide to the weak acid, you'll make, instead of hydroxide, you'll make water. Okay, what if a strong, so let's do our equation again. What if I add a strong acid? What happens? Okay, so you have you have HA in equilibrium with the H plus and the A minus. Okay, so now let's say that we add something like HCl. Again, the H is the only thing that we really care about because the H is a strong electrolyte, so it'll break into H plus and Cl minus. Okay, so what will happen is ultimately you have to remember that it's not just the proton, it's the hydronium ion that the strong acid creates. So what will happen is it'll come in, you'll add it, and what will happen is this will react, and the proton will go back onto the conjugate base and make HA. So then you don't have the dissociated acid anymore, so it won't affect the pH. So again, you'll have that hydronium plus the A minus, and what you end up getting is water again plus the weak acid. Okay, so that's sort of how a buffer works. It has two pieces. It has the conjugate base and the weak acid, or the conjugate acid and the weak base, and then it reacts with the protons and the hydroxides to avoid a pH change. Okay, so let's do an example. We're gonna calculate the pH of a buffer. So what I'm gonna do is I'm gonna use my equation here. I'm gonna use H plus is equal to that Ka divided by the A minus. Okay, now you can always just rearrange this equation, so this is not something that you have to memorize. Okay, so now to get our logs, what I'm going to do is I'm going to log both sides. So I'm going to do negative log, because you have to remember that pH is equal to negative log, right? So our pH is equal to the negative log of the H plus concentration. So I need that negative log to come from somewhere, so I'm just going to negative log both sides. So I'm going to do negative log, so then I end up getting negative log H plus is equal to, I'll eventually move this, but it'll be negative log Ka. So then what I'm going to do is I'm then going to, what's the word I'm looking for? Distribute the negative log to both this and the Ka. So what I'm going to do is the negative log of H plus is equal to the negative log of Ka minus, or negative, log of HA over the conjugate base. Okay? And then what I'm going to do is, what you'll realize is that this is the pKa, okay, and the negative log. So what I'm going to do is I'm going to get rid of these negatives, make them positive by turning this in. So I'm going to say that the pH is equal to the pKa plus, and I'm going to flip these to get that plus, plus the log of the conjugate base over the weak acid. Okay, so ultimately, to solve for pH of a buffer, you're going to take the pKa of the acid, so that's just the negative log of the Ka, and then you're going to divide the conjugate base concentration by the weak acid concentration, okay? So that's this equation that I have right here. And then this equation is known as the Henderson-Hasselbalch equation. So when we talk about buffers, it's important to note that the best buffer will occur when the concentration of A minus over HA is close to 1, right? Because you have to remember that log of 1 is 0, so then you're not adding anything to the pKa, which then your pKa will be close to the pH. So our goal is to get this ratio between these two to be as close as 1 as possible. That makes the best buffer. Okay, so let's look at an example of how we would calculate this then. So it says that let's figure out the pH of a buffer for benzoic acid, and we don't have the Ka here. So the Ka of benzoic acid is 6.3 times 10 to the negative fifth. So ultimately, we're going to figure out what is the pH of this buffer when we have these two things together. Okay, so just like what we did with the common ion, you're going to set up your equation. So benzoic acid is C6H5COOH. So it'll be in equilibrium with C6H5COO minus plus your H plus. Okay, so this is the benzoate, ion. So that's what you're going to start with here. So if I'm ricing this, I'm starting with 0.12, and here I'm starting with 0.20, and this is 0. So then your change is going to be minus x plus x plus x. So this is going to be 0.12 minus x, 0.20 plus x, x. So then the Ka, which is that 6.3 times 10 to the negative fifth, is going to be equal to that 0.20 plus x times x divided by 0.12 minus x. So the x's here cancel. So then I have that equal to 0.20 times x divided by 0.12. Okay, so then I'm going to multiply the Ka by the 0.12, and I end up getting, 0.20x is equal to 7.56 times 10 to the negative 6. So I divide both sides by 0.2. So x is equal to 3.78 times 10 to the negative fifth. Okay, and then this is the concentration of H pluses that we have. So then you can just take the negative log of that to get the pH, and I end up getting the pH of 4.42. Okay, you can also use this equation that we just did up here. So you would do the pKa, so you would do the negative log of the Ka plus the log, and then you would do the 0.20 divided by the 0.12, and you'll get the same answer as 4.42 pH. Okay, so that's it for buffers. We'll do some examples of this in class to make sure that we understand what we're doing. Thanks.